So what did we find? Ux is equal to ui and ui is minus x. So Cauchy-Riemann equations hold it. Okay? For every x and y. Okay? On the complex plane. But I will qualify these statements later on. Think of it a bit more. Think of it a bit more. Because why? What if you are at infinity? Right? Because then you are comparing infinity with infinities. Then it doesn't make sense. Right? Okay? So we'll take that up later. But for now, this is fine.
Yes.
Okay. So this is an analytic function indeed. Let's go ahead. We can also do mappings. Right? Remember yesterday we did some mappings. But not here because these look very complicated functions, and you can do it on a computer if you wish. So there is an online program, online app to do where you put this function and you draw something. It tells you how it looks there. Just remember there are two planes. One contains inputs and contains outputs f of z, which you know is just p of z this guy. So if you input a circle, it will get mapped to something I don't know. Right? It might not be easy to figure out that shape. The shape. It's easy to figure out the equation for that shape. Right? But it might not be easy to figure out what that shape is. So you can use a computer. Okay? But we'll do some simple ones. Okay? We'll do some simple ones. So this is polynomial. So any polynomial would be analytic. Right? Okay. Good. Let's take up another trigonometric functions. Okay. So let's say sine. So you did sine x, cos x, and what? Sine x, cos x, what? And tan x, right? So now we consider sine z. How do I define sine z? Right? Z is a complex number now. Okay? Remember, how did you define sine x? You can't use perpendicular by base. You're no longer in class 10, right? You can use perpendicular by base, right? But I mean, it gives you angles still some 90 degree, right? Then you extend that, remember, periodically, in certain way, certain manner. But there is one definition which easily extends because this is a complex number now, so there is no triangle and all. पर आप angle बना सकते हैं. Z is no longer an angle; it's a complex number. Right? So there is one definition which naturally translates to a generalization, which is, remember, sin x was what? E power ix. If x is real, right? Minus e power minus ix divided by 2. Right? So I just defined the same thing. E power z is minus e power iz minus e power minus i. Yeah. Should be okay. If z is real, then it reduces to this definition. Okay. So this is the definition of sin x, sin z. Obviously, if z is real, then this gives you the sin x, the real sin x function, right? Similarly, I can define what? Cos z equal iz minus 2i. So sin that 2i is the number. Okay? So these are basically the complex. Is it analytic? Yes, it's analytic. Why? There's no such stuff. I'm writing function of z. As long as I write function of z, they will be analytic. Right? What about real and imaginary parts? Let's do sin z. What about real and imaginary parts? E power I, z is what? X plus I y minus e power minus I, x minus I y divided by 2y. Okay? What do I get? What do I get about the real and imaginary part? 1 by 2i e power ix times e power minus y. I just multiply. Minus e power minus ix e power minus plus I just carry minus 1. this should be plus. Yeah, I'm so sorry. Yeah, x plus I1. And then what do I get? Plus 1. Okay? Now x is real. Right? So remember we have this identity for real x. E power I x is what? Cos x plus alpha sin x. Remember? E power I theta. Right? I can't use it for this. It's not. Okay, first I mean this is. There's no alpha here. Okay? But I can't use this directly for this. I can't write this as cos z plus alpha sin z. Right? Because z is complex. We derived the relation for what? Real. So I can write e power I x as what? Cos x plus I sin what? X. E power minus 1 minus cos x minus I sin x. Because sin of minus x is right? Minus sin of x. E power 1. And what do I get? What about real and minus 1? 1 by 2 I have what about the real part? It's cos x e power y minus y plus. You just collect them. Okay. Cos x e power minus y minus e power y plus alpha sin x e power minus y plus e power y. This thing. Okay? Now, this guy e power minus y minus e power y divided by 2, and this guy e power minus y plus e power y by 2. These guys are very similar to the sine function, right? Huh? But now your argument here, this is purely imaginary, right? So you are writing iota 1, right? Something like that. Iota 1. Okay? Fine? This is okay. Such functions are called hyperbolic sine and hyperbolic cosine. Okay? So sine hyperbolic of x is defined as e power x minus e power minus x by 2. And cos hyperbolic of x is e power x minus plus e power minus. These are real functions. Okay? And they are extensions of they are basically okay. When you did real line, you have sine and cos, then you do this. Okay. Remember, here there is a simple factor difference. When you define sine hyperbolic of x, you don't put iota. You don't put iota. Okay. Okay. This is a bit different from sine z. Okay, is it fine? And I would expect you guys to plot these functions and see how they look as exchange. Okay. Plot sine hyperbolic of x because it's a real function and you should know what their plots are. Plot that. Okay. So this is like you can also do cos z now, right? I don't need to do. But let me do two important functions and then maybe you can move ahead because already 11.
So I think cos is e iota z plus e times minus i.
Yeah, it's plus. Yeah, okay. Yeah, thanks. Yeah, thanks for pointing it out. So e power I z plus e power minus I. Now you can figure out the real and imaginary parts of cos z, right? Let's do another function. Okay. It's logarithmic function, huh? Okay. So here I won't use x plus iota y. I would use the polar form because it's easier. Okay. So this is log what r e power I, where r is equal to mod z, and theta is what? R tan like this. Dy r. Okay. Now this guy I know, I mean this is just product, right? This is log r plus iota theta. Because log e power iota theta is wrong. Iota theta will come in front and log e is just 1. power iota theta, e power iota theta plus 2 pi, e power iota theta plus
4 pi.
huh? Right? All of them will give you different answers. Right?
Yes.
Huh? So look at the imaginary part of z, imaginary part of log z. It is the argument directly. This is the argument, the angle of the argument. Right? So if you take, let's say, if you take r e power iota theta, your log is what? Log r plus iota theta, right? Good. Fine. But if you take log r e power iota theta plus 2 pi, this is the same number, right? This is the same complex number, log z. The z is same, right? There is just same representation. But what do we get for the log? It's log r plus what? Iota
Theta plus 2.
theta plus 2 pi. Fine. So you see, you get a different complex number. From that? Huh?
Yes.
So all different representations give you different complex number. Huh? Is it okay?
Yes.
Now let's try to visualize a bit more. So let's make these two planes. One, there's that plane. Another one, the f of z plane. Okay? So any point here, r e power iota theta, goes to a point inside. But what is the y-axis? It is the imaginary part of f of z, which is just what? It's just theta. It's just this theta. Right? We just learned. What is the real part? It is log of this length, log of this length. We get the point. Huh? Fine. Now, see, when I change, let's keep r fixed. Okay?
Yes.
So it means we are going on a circle, in a circle. Let's see where does this circle go. Right? So if r is fixed to some number, let's say r is 3, it goes, and I am just varying theta, right? Where will this point move? If I am varying theta, which way will this point move? So r is 3. So r is 3, so I am at log 3.
Yes.
So I am here somewhere. And I am not allowed to move like this. Why? Because r is fixed. Right? So you are mapping this z to w. Right? W is f of z. Right? And you know argument of the imaginary part of z is just theta, this thing. And the real part is log r. Remember?
Yes.
So now I am fixing r here. So when I keep r here fixed, which way am I allowed to move? I am not allowed to move like this. Maybe because that will change r. Maybe it will change log r, so that will change r. So which way? Up and down. So a circle gets mapped to what? Line. A line. A line parallel to what? It is the imaginary line in f of z plane. No, not really imaginary. This is not imaginary. Imaginary line is right? Yeah, that depends on r. So now if I change r, I will get another line. If r is 1, let's say, then log 1 is what? 0. Then I get this. Okay. Is this clear? Huh? Unit radius gets mapped here. If r is less than 1, then log r is what? Is it positive or negative? It's negative. When your number is less than 1, its log is negative.
Yes.
Just think about it a bit, huh? So now it means the circle of radii less than 1 are mapped to lines here. Their position is negative. And circles of radius greater than 1 are mapped to lines here.
The pulses.
So can you visualize the mapping now? Huh? These circles, so let's say this is e power iota theta, so r is 1. So circles inside will go here on this side.
And circle on the
Outside will go that
side.
Okay? So what does log z do? It maps inside points this plane on this plane, this side of the plane, and outside point on this side of the plane. Okay? Is this clear? Huh? But we should be careful, right? I drew a line stretching from minus infinity to infinity, right? But theta goes from just 0 to 2 pi. 0 to 2 pi.
Yes, sir.
You know? So I can't draw a line from minus infinity to infinity. Theta value is only till 2 pi. Right? 0 to 2 pi. So I should cut it here. Is this clear? Is this clear? Now this region is mapped to what? Circle outside, inside. Outside. Right? So our log r is positive, so r is greater than 1. Yes. You log r axis. Right? Okay, which is the real part of the function. And this region is mapped is this. Okay? So this is mod z less than 1 region, and this is mod z greater than 1. Okay? So what about the rest? Where does the rest of the complex plane go? How do I get this point? How do I get this point? How do I get this point? I mean, I've exhausted my complex plane here, right? There is no other point left. Right? You just saw, right? Circles inside, any point inside would be on some circle inside. This region gets mapped to this region, and that region, the outside region, the entire gets mapped to this. What about this? What about this guy? Right? Theta. One second. Theta. I have to increase theta beyond 2 pi. I have to increase theta beyond 2 pi. Right? So in order to exhaust this complex plane, I need to take another sheet. Right? Where I am repeating z values, but these values won't repeat. These would be the same values, but this would just shift by 2 pi. Right? 2 pi. I have done 2 pi, adding 2 pi. Right? But how many such sheets do I need to take to exhaust? Infinite. Right? Yes, sir. Infinite. Right? Because if you just take 2, you will cover this. Okay, then one more. 2 pi to 4 pi. Right? 2 pi to 4 pi. 4 pi. Huh? And there are negatives also, because you can either rotate clockwise or you could counterclockwise. Is this clear? Huh? Right? So can you visualize logs and mapping? Huh? Huh? Okay, good. So in order to exhaust this, complex plane here, my function f of z, I needed to take multiple sheets. Huh? Make a point of this. Then I need multiple sheets. Right? Later on we'll see how to join these sheets. Okay? To form something called Riemann surface. Okay? Later on we'll figure out how do I join these sheets. Because right now it seems I have to go from 0 to 2 pi, right? But I can't go beyond this because I will end up on the same plane. Right? I need to consider another plane where angle starts from 2 pi. Right? We'll later on figure out how to join these. Okay? Huh? Now people typically select a principal region, right, to work with. Because you don't need to work with every point. Right? Because you're just repeating. It's the same value, right? And people typically choose it from minus pi to pi. Theta from minus pi to pi. Which is I chose this from 0 to 2 pi because it was easier. But I can also choose minus pi to pi. It will cover one plane, right? Which will cover a region where the origin is here in the middle. Nothing special. Okay? And this is just a choice convention. Okay? And it's called principal. Principal axis. I'll tell you later. I don't remember. Okay? Right? So do you understand logs and maps?
Yes.
So circles, logs and maps, circles to lines. Okay. Okay. What about lines? If I take a line here, what does log z do to that? If I take a line on z here. So taking a line means keeping theta fixed. So if you keep theta fixed,
Log R.
huh? You can only change log r.
Line.
Right? Yeah? So if you keep theta fixed, it means here you are fixing imaginary part. Here you are fixing an angle. Right? Angle, so it means you are allowed to move on this line. Right? But that does not allow that here and you're allowed to do like this. You're allowed to change all that. Right? Okay. This part of the line, this part which is inside mod z equal to 1, right, is mapped to this entire thing till infinity. Huh? How is it possible? I mean, this is such a short thing, right? And this is a line from what from 0 to 19. You learn that okay, I'll tell you later. Because if you have this and you want to map it to this, what do you need to do? What do you need to do? Stretch, right? Make a point of this. I'll come back to it. Okay, you need to stretch. Okay? Right? And also, you want to make this line is tilted, you want to make it parallel to this, right? You need to stretch and rotate. Right? So, if I stretch and rotate, I will get a line here. I also need to shift. Right? 3 things. Stretch, rotate and shift. Okay. Fine? Is this all right?
Yes, sir.
Good. Okay, so do you get the physical operations that are happening, right, while you're going from this to this? You're stretching, rotating and shifting. Right? Huh? I'll show that indeed that's all you are doing. There's nothing else going on. Stretching, rotating and shifting. We'll see it later. Okay, this is fine, right? Log z is done. Let's do e power z. Okay, e power z is just inverse of log, so I won't do any mappings here. Okay? So e power z is just e power x plus iota y. Okay? What is that? E power x cos x plus iota. Cos y plus iota sin y. Right? Why did I split it before applying De Morgan's formula? Because e power iota y is cos. And e power x is just a real function. I can't write it as cos x plus. There is no iota real function. This, okay? Now, it's invertible. So, e power x would take, see, f of z is e power z. Let me call this f of z as some number w. It means z is what? Log w. If z is not w, so the inverse will happen. If you take a line here, if you take this line, it will get mapped to
Just the reverse of the order.
If you take this line, it will get mapped to
Circle.
with the same line. And is it analytic? Is this guy analytic? E power z is log z, is it analytic? Yeah, this is analytic. Okay? Yes. By the way, log z has an issue. It's multi-valued. Right? For the same z, it gives you 2 different answers. Okay? It's a multi-valued function. Okay? But we'll come back to that later. Multi-valued function. We'll do that later. Okay, is this fine? So, if you want to invert, right? If you want to invert, you can't invert on the entire complex plane because it's multi-valued. Right? So you have to stick in a region, right? 0 to 2 pi. Just invert in that. When I said invert. Okay?
Yes.
So line here would get back to circle there. Two things, yeah. To continue. We'll just check it and wrong one. Okay, good. So let's do one more thing. Let's do f of z equal to z to the power 1 by 2. Okay? But this is what? This is analytic. Why? You don't need to check CR equations. Huh? Yeah, we can check, but we'll give you the same thing. Huh? Okay. For now we are saying is this analytic, we say yes. We need to. There would be certain points, even if your function is a function of z, there would be certain points where it may not be analytic. Right? For example, if you take f of z equal to 1 by z, okay, and then you want to check its analyticity at z equal to 0. the function is not well behaved at z equal to 0. Okay? So I'm already giving you a sneak peek of what I'm going to tell you, that these functions should be well behaved. Right? The points at which the function takes infinite values, right? There the function is not analytic, because then your derivatives become infinity, everything becomes infinity. Right? So Cauchy-Riemann conditions of f of z equal to 1 by z won't make sense at z equal to 0, right? Because it's infinity both sides. Right? It's minus 1 by z square when you put. Okay? But just pick a pause on that. We'll do that efficiently. A z to the power 1 half, okay? Which is r to the power 1 half equal to I am using polar form. Polar form is easy. I will just tell you to do it. Let's do z thing and f of z. And what does z go to? If z is here, let's say, at some r and theta. Okay? What does it go to? This point? It goes to r to the power 1 half and theta becomes r. This is w equals to f of z. W is same as f of z. I'm calling w equal to function of z. W is a complex number, is a function of z. Which is square root of z. Okay? Can you notice one thing here? Can you notice one thing? If I go through this entire
Surface.
if I go through, let's keep r fixed and where is theta? I will cover a circle, right? But here what do I get? I get semicircle. Right? R is fixed, so this r to the power 1 half is fixed. It is half. Right? What about the rest? What about the rest? Because this whole thing is, this whole complex plane is mapped to the upper part. What about the lower part? Yeah.
2 pi. 2 pi.
Exactly, you need to add 2 pi, right? So, do you add 2 pi? So I add 2 pi, so I get one more complex plane, right? So 2 complex planes I need in Z to cover this entire thing, right? Just 2 or more? Just 2. So once again, you need 2 sheets to cover this entire thing. So this is also multivariate function, like for 1 half. It gives you different answers for r equal to theta and r equal to theta plus 2 pi. Because when you get 2 pi, when you divide by 2, this will get theta by 2 plus pi. So theta by 2 plus pi. So you will get 0.6. Okay? So how many sheets you need? 2 sheets. Okay? And then later on you will learn how to join them. How do I join these? Okay? Then you will have a one surface and you are taking a function from that surface, talking about a function from that surface. This, right? For now, you can just think about 2 sheets, and those 2 sheets allow me to map the entire complex. Okay? Let's do the last thing today. Okay? Then we can do some random problems. Okay? Remember, I told you that when I told you that this analytic functions, they are free from that stuff, right? In fact, you only calculated that, right? So if these analytic functions are free from z star, that means that derivative does not depend on direction. Otherwise, you would need to specify a direction. Huh? It does not depend on direction. Okay. Now we'll see an interesting consequence of that. Okay. So imagine you want to find, before that, let's say if I give you 2 complex numbers, how do you find an angle between the 2? If I give you some z1 as r equal to theta 1, r1 and z2 r2 equal to theta 2, how do you find the angle between the 2? So remember, I can think of these as vectors. So I have z1 and z2. Right? How do I find the angle? This guy. How do I find the angle? Obviously dot product, right? We can do dot product. but there is a simpler way. I know the argument of this one, I know the argument of this one. I just subtract, I get this angle. So argument of this one is this angle, right? This is theta 1. This is theta 2. The angle is theta 1, theta 2 minus theta 1. So argument of Z1, sorry, angle alpha between the two is argument of Z1 minus argument of Z2. Which one is bigger? Positive and negative. Depends on which way you are taking the angle, this way or that way. Right? Okay. One more important. What if I divide the two numbers? What do I get? Z1 by Z2 is what? R1 by R2 equal theta 1 minus theta 2. This. Huh? So argument of this, the division of these two complex numbers. Division is multiplying with the inverse. So this is basically argument of Z1 by Z2. Okay? This is a relation between arguments. Have you seen this earlier? You should have seen this earlier. Yeah, maybe not, it's okay. But argument of Z1 by Z2 is equal to what? Argument of Z1 minus argument of Z2. Okay? Yeah, it's a very simple relation. It follows from argument. Good. Let's try to find angles. Okay? What happens to angles? Okay. So I have a complex plane here. I have a complex plane here. This is my f of z. Right? Where things are going. This is it. I'm at a point here. Huh? I take two small directions. Delta z. This is delta z1, delta z2. Remember? Right? I'm drawing vectors, small vectors. Delta z1 means delta x1. It will specify a vector which is split by direction. The reason I'm going back to vectors again because you just learned vectors. So, do you agree why I'm writing delta z1 and delta z2 with different vectors? Now this guy, this strip, if I take this strip, it will map to something, right?
Yes, sir.
This delta z strip. And these points, and the points on here. Yes. It will map to something. What? Maybe delta f1. And I'm sitting at the same point. This point maps to this point. So this point maps to this point. And delta z1 maps to delta f1 and delta z2 because of this function. Okay? Huh? Yes. Huh? You will shortly see what is another consequence of this derivative becoming independent of direction. Okay, there is an angle here, right? Alpha. There is an angle here as well, right? Phi. Huh? Right? I want to know what is the relation between them. Right? So what should I do? I should find argument of the ratios. Right? Okay. My theta is just argument of what? Delta z1 divided by good. And my alpha phi is argument of what? Delta f1. But what is delta f1? We just computed how to compute the change. What is delta f1 complex number? Remember? Shall I go back? Delta z is this thing which was the derivative df by dz plus delta z star and this thing vanished. Right? We're assuming analytic functions. This thing vanished, right? So what was delta? It is the derivative times what? Delta z. So this is df by dz computed where? At this point, right? At this point, z, computed at z. I'm calling this point at z. Computed at this point times what? Delta z1. Yes. Okay. is delta F2? Computed at this point times. Okay? The function is analytic. Right? That allows me to say that this is same as this. The direction does not matter.
Yes, sir.
Right?
Yes.
We have assumed that this is analytic here. We work with analytic function. When I take the ratio, delta F1 delta this and this cancels.
That is it.
Only because direction does not matter. Right? Huh? Right? So what do I get? This and this cancels in the ratio. What do I get? Argument of delta F1. So what does, whenever we make the mapping by complex functions, analytic functions, it does not change local angles. Okay? Right? If you don't want to change local angles, if you are not allowed to do that, what can you do? You can rotate it. Obviously rotation does not. Right? What else? You can shift. Right? You can shift. Right? What else? You can stretch. Right? There's nothing else you can do. Huh? But you get one more. You get one more thing. You get one more extra benefit. That you are allowed to rotate different amounts at different positions. And you are allowed to rotate different amounts, you stretch different amounts at different positions. Do you get my point? Huh? Right? See, you can either, okay, when you shift, you can shift the entire thing by, let's say, entire thing. Let's say if I am considering some mapping, okay, let's say I am considering mapping of this region. Okay? Using some complex function. Okay? Now that complex function, using some analytic function, okay? That analytic function can end up shifting this. Okay? But it can end up shifting this entirely, like wholly as well. But it can shift this guy a bit more and this guy a bit less. Okay. So you are allowed to shift by different amounts. Okay? Huh? Also you are allowed to rotate by different amounts. Okay? Okay. Let me just quickly do this and then probably stop maybe. So let's take f of z. F of z equals multiplying a complex number with itself. Okay? Huh? What happens when you multiply two complex numbers? Okay? It's very obvious. See? Let's say you multiply z1 with z2. Okay? Huh? That is what? R1, R2 e power R2. Okay. Huh? So what's exactly happening? So your z1 was something, z2 is something. This z3, which is product of z1, z2, right? It has a magnitude. It has a what? It has a modulus of mod r1 into mod r2. Okay. Yes. And it has an argument what? Theta 1 plus theta 2. Right. So let's say I have z1. I multiplied it with z2. Z1 had its own R1 and theta 1. I multiplied with Z2, I get Z3. Right? What kind of operations, physical operations should I think? So there to go from here to here. A, I rotate.
Yes, I split.
I rotate because I want what? I want the argument to increase. So I rotate. But R1 will remain same if I just rotate. I want to stretch. Now see what we are doing here. You are multiplying z with z. So at every point, you are rotating by how much? The argument of. So how much did you rotate here? The argument of theta, z2, right? The number which you are multiplying. What are you multiplying here? Z itself. So at every point you are rotating by how much? इसका जितना argument होगा, वो different होगा ना हर जगह. So you are rotating different amounts. Okay? And every point you are what? Stretching by जिसका जो you get my point? So this rotation and stretch is different at
different points.
Okay. Huh? By the way, this angles, right? So you're allowed to what? Rotate, stretch, or shift. These three things are called conformal mappings. These are called conformal mappings. We'll learn a bit more about conformal mappings and why they are important, but for now the definition is up here. I think you are in a position to understand this. What is a conformal mapping? Huh?
That's my angles preserved.
Just my angles preserved, the local angles are preserved, okay? Huh? It's not, there are other structures, mathematical structures where you see conformal mappings, okay? But all analytic functions are basically what? They're conformal maps, they're conformal. Okay?
Yes.
Good. Why? Because they preserve angles. Right? And you can do amazing things with just these three options: shift, rotate, and stretch. Just amazing things. Okay? Huh? Right? I'll tell you one thing, but this you don't need to understand. You just take it at its face value. Okay? You can map. There is a complex transformation. There is a basically analytic function, a complex function, the analytic function, or a conformal mapping. It's the same, right? In this 2D complex plane, which takes a polygon. It takes a polygon and maps it into a circle. This is mapped here. This guy. And it has tremendous applications. This is called, and this transformation is called just a name. Okay, it's called Schwarz-Geschulte transformation. Okay, it's called. I won't write the exact function. Okay, there would be a function, right? Huh? There will be some function. It's a bit complicated. I won't write that. Okay, that will just confuse you. But just remember this: that it is possible to map polygons to circles. Interior of the polygon will be mapped to interior of the circles. Okay, it's called Schwarz-Geschulte transformation. Okay, it's just it's just the reason I told you this just to illustrate you how useful this is. Okay, you will learn that this is indeed very useful. Okay. Okay? Yes, see how it is useful. I'll tell you. If you want to solve a problem in this geometry is difficult. Right? So many. Right? So many bands and all. It is difficult. Right? What do? You solve the problem here. Nice circle, right? Once you are done, once you get the solution, you go back. Right? But for that to be possible, my conformal maps, right, my analytic functions have to preserve solutions. Right? Have to preserve solutions. But solutions of what? Or solutions of what? Right? You just agree. You should have asked solutions of what? If I am solving some equation here, okay, where I have to deal with a boundary like this, right? There is sometimes you would have, the solution depends on what kind of boundaries you use. Right? Huh? It would depend, right? Because this will thing you need to take into account that there is a boundary, there is something there, right? This should reflect in your mathematics, right? So if there is an equation which you have to solve with this boundary, okay, this is difficult. Okay, you solve that equation here with this boundary and go back this time. But for that, the solution of the equation should remain preserved, right? If you do a analytical transformation, right, the conformal transformation, it should not change what? The solution to the equation. Okay, now we'll learn that. What kind of equation? Which equation am I talking about? Okay, huh? It's really simple. So what do this guy give you? What does this guy give you? See our equations. It gives you ux minus 2y, right? The derivative of x with respect to x. And this equals y. No, minus. ux is vy, right? And uy is
minus vx.
minus vx. How about uxx plus uyy? So if I differentiate with x, what do I get? vxy. है ना? ये समझ में आ रहा है ना? This is a derivative, double derivative, right?
Minus vx.
Minus vxy. So this one. So if a function is analytic, it automatically satisfies this equation. What equation is this? Have you seen this equation somewhere? Where? Yes.
Exactly.
Huh? Which equation? Huh?
Euler's equation, exactly.
Oh no. This is Laplace equation. Okay? Huh? This is Laplace equation in 2 dimensions. Huh? So all real and imaginary parts of a complex of an analytic function. You can also show that, okay, if you do this at your home, that d square v by dx square with just the same value. Okay? Huh? So real and imaginary parts of what analytic functions? Huh? No, first listen. Real and imaginary parts of an analytic function satisfy what?
Laplace.
Right? CR equations guarantee this. Okay? Is this correct? Huh? So as long as my function is analytic, I am guaranteed this. Right? Now let's go back here. If I am solving Laplace equation with this boundary, okay? This is difficult. It is difficult. Right? Huh? But if I make a transformation and solve it here, it is easy. Huh? But as long as my transformation is analytical, right?
Yes, sir.
I am guaranteed the real and imaginary parts here of this function. Right? So I have a solution here, right? Psi, right? Psi is a function of, like the solution here, there is solution u and v. There are two solutions, u and v. Okay? And both of them put together gives me f of z. Gives me f of z. Okay? This is difficult to find f of z. Right? Because Laplace equation we have to solve with this. Now, instead of f of z, I change z to some, using this Schwarz-Christoffel whatever, that like cryptic transformation that I just wrote on the board. It just maps this polygon into a circle, right? Huh? So I can, instead of finding f of z, I can find f tilde whatever of omega of z. Right? But this is analytic. Right? Once I have this, I can invert and then find f of z. Is this clear? But what guaranteed that this is indeed a solution to the Laplace equation? The analyticity, right? CR equations, which is, so as long as the function is analytic, so this is how it's used. There's nothing concrete I am doing here. I'm just telling you, I'm just illustrating an idea where this conformal transformation is used. Okay? Conformal transformation means it preserves angles, and analytic functions give you conformal transformations. Okay? So they are just combination of three things. What? Rotation, shift. There is one more thing which is inversion. We'll see that later. Inversion means you take a circle and all points outside you take inside, all points inside you take outside. That's also basically that's inversion is maybe also a combination of, I think. Just do that later. So, okay? And you agree with me that that's indeed we are doing. Okay? stretching by different amounts at different points. That's why you get these weird things. A circle goes to a line, right? A line becomes a circle. You'll see many more things. You see many more things. Okay? Huh? And you can see a small piece getting mapped to a large thing, right? It's because stretch can be arbitrary. You can stretch as much as you want, and you are allowed to stretch at different things. How about so the real and imaginary parts of an analytic function satisfy what? Laplace equation. I want to say one more point. I want to tell you is that if and then probably we can end this. So I told you that if these are true, if CR equations are true, then this is guaranteed. Laplace equation is. Yeah. U and V will be solutions of Laplace equations. Okay. Good. But what about the other way around? If you are given solutions of Laplace equations, two solutions of Laplace equations, right? If you are given two solutions, would it be? Would it satisfy CR, or would the function that we define with these two solutions be analytic? The answer is no. The answer is no. And no, I can just give one example and then that should settle the thing. Okay? How about u equal to x? Okay? Is this a solution to the Laplace equation? Huh? If I do double derivative of u, it's 0. Double derivative of y, there's no y, is 0. And let's say b is 0. Is this a solution? It's a solution, right? But is this function that f of z that I define, which is this x plus iota 0, u plus iota b, is this analytic? No, because x is what? Z plus z star. Right? So this is not true the other way around. If you come from above, it's true. Give me CR equations, then these are guaranteed to be solutions of Laplace equation. But given two solutions of Laplace equations, it may or may not be. The u plus iota v may not be, may or may not be analytic. Okay? Right? Yeah. So all the functions that we wrote, okay, they are basically solutions to Laplace equations, right? With some boundaries. Okay? So how about log z? Would this be a solution to the Laplace equation? Yeah, it's real and imaginary parts. Let's find its real and imaginary parts. Its real and imaginary parts is log r plus iota theta. Okay? Okay? Theta I leave for now. This is 1 log of what? Log of half of x squared. Okay? Huh? This is fine. Huh? Okay. So this has to be a solution. Theta is tan inverse phi. So this has to be a solution to the Laplace equation half log x squared plus y squared plus iota tan inverse. This also has to be a solution to the Laplace equation. You can check. You can check. Why? Because this function analytic, it gives me CR. CR tells me that u and v are solutions to the Laplace equation. Okay. Now let's keep a pin on this. Okay. Huh? Let's do some electrostatics. Okay. Huh? If you have a point charge, okay, in 2 dimensions, okay, let's say I have a point charge, but I'm living in 2D world, no z, okay. How do I find the electric field due to this point charge? Like Coulomb's law, right? But now you have 2 dimensions. You don't have 3 dimensions. What is Coulomb's law in 2 dimensions? Okay, let's do simpler one first. Let's take 3 dimensions. How did you find electric field due to a point charge? It was Coulomb's law, right? 1 by 4 pi epsilon r. So electric field 1 by 4 pi epsilon point charge and origin, right? 1 divided by what? 1 divided by r square. R hat. Huh? Yes, sir. Indeed, right? Q. Q. Okay, let's say this is 1. Q by 4 pi epsilon. Q is 4 pi epsilon. Okay, there's this one. Then there's the R hat there. R square. Right? This is my electric field. Right? But this was Coulomb's law, right? For 3D. How do I derive it for 2D? Okay, if I want to derive it, what law should I use? Gauss law, right? In 3D, what did you integrate on? Sphere, right? What should you integrate here on? No. So in 3D, once again, in 3D, you integrate over a sphere. Why? Because perfectly symmetric about the. Huh? Circle. What should I integrate over a circle? What did you integrate over a circle? What did you compute? Flux. Right? 3D man, you computed flux.
Yes.
Yeah, 3D man, let's do 3D first. Integral E dot ds is what? Q by epsilon naught. This is Gauss law, right? Okay?
Yes.
And ds is what? I need to take arrangement on a sphere, right? And do the dot. What is the normal? Normal is r hat. So long r hat, right? So this will give me er, the radial component of the electric field. Time is r dr. Time is what? R dr d theta d phi, right? But there is sin theta also. But there is symmetry, right? ER, the radial component of the electric field, has to be the only non-zero component first. Second, it should not depend on which point we are talking about. Because the point charge can't distinguish between this point and that point. Right? As long as it is. So, R square, yeah. So, ER will come out. Right? It does not depend on anything. Yes, sir. And this thing will integrate to what? Oh, no, wait. No, this has dimensions of volume. I need to take arrangement.
So same thing.
D theta d phi. Yeah, d theta d phi. R square sin theta. D theta d phi. R square. There is sin theta also. Right? So remember, I told you how to get the arrangement on this. And that gives me Q by epsilon naught. Right? It's because of symmetry this thing gives me something more complicated. Otherwise, it's very difficult to figure out electric field from this. It's because of symmetry. Now, ER will come out and this thing will become surface area of the sphere, which is how much? 4 pi? 4 by 3. No, that's 4 pi r square. I might need to cut this part out. 4 pi r square. 4 by 3 pi r cubed is this volume. Yeah. So, ER. Okay? Times what? 4 pi r square is what? Q by. And then let me give 1 by 4 pi epsilon naught Q by r square. Okay? And it's in radial direction, r hat direction. Okay? Fine? Let's do the same with this here. What do I get in 2D? What do I do? Integral E dot?
Yes.
There's no ds. dl. No. dl. Earlier you were integrating on a sphere. So there was an arrangement on this sphere. Now you are integrating on what? Circle. Right? Because you are in 2D. You have to integrate on this line here. Right? So you have to integrate E dot dl. Yeah? But that's equal to what? That's equal to Q by epsilon naught. Once again, only radial component would be non-zero and it would not depend on where you are. Right? So this will give me E dot dl. dl is along this and radial component perpendicular. So dot product is what?
0.
No. E dot dl. No. Sorry. dl. You can't take. Okay. dl. The direction of. Sorry. This. Think of the area element again. There was an area element, and then we took its direction to be perpendicular to this. You take direction to this. Okay, you have to integrate with this. Right? It's not the length element. The length element has the same direction. as this strip, right? But if you generalize from 3D, it has to be, you take the direction, right? You take area inverted 2D, which has the direction perpendicular, right? Now this will be what?
Yeah.
Integral E dl, whatever this length is, okay? I can put it in polar coordinates, fine, that will give the same answer. E is this component around this, is the only non-zero component equal to Q by
Epsilon.
but E will come out, but integral dl, when you add these, all these small strips, what do I get? Huh? If I add all these lengths,
2 pi.
2 pi r, right? Not pi r square. Yeah, 2 pi r. 2 pi r, Q by 2.
Yeah.
What do I get for E?
1 by 2 pi epsilon.
Q by 2 pi epsilon naught. This is electric field in 2D, Coulomb's law in 2D. Okay? Right? It's just simple generalization. Okay? I mean, in 3D we are going on a sphere, in 2D you take area element on a circle. So direction का थोड़ा ख्याल रखना है. ठीक है ना? Because you might confuse it with anything. Okay? Just like I did for a while, for a short while. Good? Huh? What about potential? What potential will give me this? Which potential? Sir, remember electric field comes from a potential, right? You can define a potential. Right? Which potential? किस चीज का डेरिवेटिव will give me q by 4 pi epsilon naught, q by 2 pi epsilon naught? This is just a constant, but type number, huh? E. So psi is d. Sorry, E should be d by d psi by dr. Gradient or the derivative of the electric field. Okay? What function should I use here so that I get q by 2 pi epsilon naught times r? किस function का derivative is 1 by r? Log. Exactly. Log r. Right? So psi should be what? Q by 2 pi epsilon naught. Does this look familiar? Okay. See, it's the real part of log of z. Huh? Right? Right? So the real part of log of z is what? The electric potential due to a point charge in 2D. Huh? Right? Okay? Huh? And you know that electric potential satisfies Laplace equation, right? Right? Just revise Maxwell equations. Electric potential, when you don't have any charge at points where there is no charge, there electric potential satisfies what? Grand square psi equal to 0. Right? Okay? So therefore, any analytic function you write, its real part as well as imaginary part would be solution to some electric field. You may not be able to figure out ये कौन सा सिनेरियो है जहाँ इलेक्ट्रिक फील्ड ऐसा होगा, जहाँ इलेक्ट्रिक पोटेंशियल ऐसा होगा, but it is a solution, a valid solution. Okay? So what did you learn? The real imaginary part of the log z is a the real part of the log z is what? Is potential due to point charge. Okay? Is this clear? Huh? Is it clear? Huh? Right? So just to quickly summarize here, the CR equations guaranteed Laplace equations. Okay?
Yes, sir.
And analytic transformations leave what? Leave and make. I mean, if I do an analytic transformation, right, it leaves the solution. It means because if I have an analytic function, right, if I have f of z, and I substitute instead of z another analytic function, so g of omega, this whole thing is analytic, right? There is no omega star. It means there is no z star. It means there would be no omega star, right? So this is the solution to the Laplace solution is this. But this might be easier to figure out. Okay. Okay. CR equations guarantee Laplace equations, but the converse is not true. Laplace equations will not be guaranteed. Okay. And then we learned that I just give you one example where I just give you this example of log z. Okay, this maybe I should have used this much. I just gave you the example of log z, which is what the solution for Coulomb law, Coulomb potential 2D. Okay, so this is it for today. Okay, let's end. Stop this.